Hello everyone. So we'll begin our discussion on the chapter of stress with the topic on traction across a plane at a point. Okay. So the first thing that we're going to do is, again, just like uh, in the previous chapter on kinematics, we are going to consider a three-dimensional body. Okay. So this is our general three-dimensional body. Now, in the previous chapter on kinematics, we were not bothered at all about the loadings that were taking place on this general three-dimensional body, but this time we will be. In order to keep the whole picture clear, I am not going to represent the various loadings that may be acting on this body, but you please understand that there will be a certain distribution of loads all over this body. Okay, now under that loading, what we would like to focus on is at a generic point somewhere inside this body. Okay, so this is a general three-dimensional body, and this is a point which is present not on the surface of this general three-dimensional body, but rather inside it. Now, we want to expose this point. The way we can expose this point is by making a plane cut through this body and passing through this point. Now, you can imagine that there may be infinite number of such planes. We are absolutely free to do that. We can have this body cut in this way, that way, any way. As long as it passes to this point, we are good. So just as a specific representation, so let us say that we are having this kind of a plane which is cutting through this body, and which is passing through this point. Let's call this point P. Okay. Now, after I've chosen this cutting plane and it cuts through this, it divides this entire three-dimensional body into two regions, region 1 and region 2. All right. What we are going to do is consider this region 2. So you understand that when it cuts it, the cross section that will be exposed will be somewhat like this. Okay. Now, I want to consider this region 1. I want to consider this region 1 with the point P exposed in it. So this is my region 1. And you understand that this region 2 will be very much present here. Okay, I am not concerned too much with region 2 now. It's something like this. Okay. Now, when I'm focusing on my region 1, especially on this point P, I consider a little area around it. Now you can understand that since I have these various loadings present on this body, when I cut out this region 1, a certain distribution of the loadings would still be present here. Now, in order for this entire part of the body or this entire region want to be in static equilibrium, there must be a certain distribution of forces acting all over this exposed surface, all over this entire plane that has been exposed by this cutting plane. However, and this is very, very important, I do not want to focus on the entire distribution of forces that is present here. Rather, I am going to focus my attention singularly on the distribution of forces on this small area A. So this is my area A and this is my point P. So I want to focus on this little area A. So I'm drawing it separately here. So this is my point P and this is my area A. Now you understand that on this area A there will be a certain distribution of forces. Let me denote that distribution of forces like this. Some generic distribution of forces. Crisscrossing doesn't matter. Now you have to understand that this distribution of forces here, only this distribution of forces acting over the region A, that is not going to balance the forces which are present over this outer surface. It is the actual distribution of forces all over this entire plane that has been exposed by the cutting plane that is going to balance these things. Okay. However, for our purpose, we are only concerned with the distribution of forces that are acting on this area A. Now, this is the most crucial thing which I believe has not been discussed earlier, and which we're introducing afresh in mechanics of solids. So what I want you to think is what will be the statical equivalent of this distribution of forces. So this is a concept that we learned in our first year mechanics, the statical equivalent of a distribution of forces, and the most generic such statical equivalent will be a single force and a single couple. So let me draw that. So I'll redraw this little area A. So even though these two areas may be looking different, I hope you can accept the fact that they are just the same thing. Okay. So what I want to say is that this entire distribution of forces will be equivalent to maybe one force. I draw it a different way. Maybe one force acting like this, or maybe like this, and one couple. So this is C and this is F. I'll put a vector over here. Okay. So this distribution of forces is equivalent to this force and this couple system. They are statically equivalent. I hope you remember something about the statical equivalency of a distribution of forces from your first year mechanics. Alright. Now if after we have that, what we are going to do is something very special. And this is where the importance of considering this little area A will be evident to you. What we are going to do now is we are going to make this area A to be very small. We are going to shrink it. So you can actually start this entire process of this entire thinking process back from here, where you consider progressively smaller and smaller areas around the point P. So you are kind of shrinking this little periphery around the point P. So we are shrinking it here, we are shrinking it here. So when we do that, what is going to happen? What is going to happen is this. As you shrink this area, naturally the distribution of forces which you see here, that is going to change, has to, because we are considering. So if you consider a smaller area here, the forces that you will see there will of course be different from what you are seeing here, which is a slightly larger area. That is what I mean. Correspondingly, if you are considering a smaller area with a certain different distribution of forces, The statical equivalent of that will also be different from what I have depicted here. Okay, so if we keep on decreasing the area to smaller and smaller regions, the statical equivalent, the force and the couple is also going to change. But along with that, you understand that in the limiting case that A actually tends to 0, okay, when the area becomes infinitesimally small, what is going to happen? What is going to happen is that it is not only the area A which is going to become very, very small, but it is also the force which is becoming infinitesimally small, because you have only a very, very small distribution of force present around here. So mind you that our current situation is like this, that you have this point P around which there is just a small area. Even this is a very large area. This is not tending to 0, but for the purpose of clarity of drawing it, I'm drawing it like this. So we have the point P, and this area has shrunk to this very, very small region around the point P. In this kind of situation, our force F has also tended to 0. Now what about the couple? Well, the couple is also tending to 0. Why? Well, you see, the couple is found out by taking the cross product between a moment arm and a force. So that kind of a moment arm would be calculated from some kind of a reference axis which may be lying on this region. Now, if we are decreasing the size of this region of this area A, the length of that moment arm is also decreasing, is it not? So I repeat, the way that this couple is calculated is effectively by taking the cross product of a moment arm and a force. If we are decreasing the area, the moment arm size is also decreasing. In the limit that A actually tends to 0, that moment arm is basically going to go to 0, and that is how the couple is going to become 0. Okay. However, you note one thing, that suppose I ask you to think about this ratio, the ratio between the force vector and the area. What about that? Well, if you think about the magnitude, the answer is not so straightforward, because area is tending to 0, the F is also tending to 0. Now what really happens, for the real answer here is that in the limit that A tends to 0, even though F is becoming very, very small and A is also becoming very, very small, it's a ratio of two infinitesimals. And as you know from your fundamental studies of calculus, that this ratio of two infinitesimals can be a finite number. Okay, so this can be some finite value. Despite the fact that individually A is tending to 0 and the magnitude of F is tending to 0, this ratio in the limit that A tends to 0, it is going to some finite value. And this is how the concept of traction is defined. So we define traction. Again, we are using the symbol for definition by using a colon in front of an equal to. So this is limit A tends to 0, F vector by A. Now some of you might be wondering, on the right hand side I have a vector divided by a scalar, so overall this should be a vector. Why have I not put a vector? And that is actually a mistake. There should be actually a vector above it. So the traction that we are saying, it is actually a traction vector. So this is a traction vector. Sometimes this is also referred to in some books as stress vector. Personally, I'm not a big fan of this particular terminology, stress vector, so I will use this one, traction vector. Okay, so when I say this concept of traction across a plane at a point, this is what I mean, the limiting value of F by A. Okay, the limiting value of f vector by a as a tends to 0. Now you see there is a very subtle concept involved here, and that is all of this definition, it pertains to this very specific point P. Okay, and not just that, this particular definition is very much dependent on the initial choice of your cutting plane. Instead of this kind of a cutting plane that we have taken here, suppose we had a different sort of orientation of our cutting plane. In that case, the exposed surface here would have been different. The region A that we would have considered would have been different. The entire story would have been different as far as the values are concerned. So the finite value that we would have ended up with had we chosen a different cutting plane, even if we had been sitting at the same point, that value would have been different. So, and certainly if you take a different point, even if you choose the same cutting plane but choose a different point, certainly the value is going to be different. And even if you are sitting at the same point, this is very important, but you take a different cutting plane, the traction value is going to be different. So the traction is very much dependent on two things. First, the position itself, and second, the orientation of the cutting plane which is generating it. So in other words, what we can say mathematically is that the traction depends on the position vector of the point of concern. It also depends on the unit normal of the plane which we are considering. So really what we should be writing here is this. So instead of just this, we should be really writing this as P vector being a function of the position vector of the point P. So x vector denotes the position vector of the point P and the unit outward normal to the plane that we are considering. So the unit outward normal, so you can think of it like this, that the unit outward normal here is something like this. This is the unit outward normal. Okay, so this here is my unit outward normal. Okay, once you have chosen your cutting plane, the unit outward normal does not change even if you keep on shrinking or enlarging your area. That is very important. The moment you have decided on your cutting plane, that uniquely determines your unit outward normal. So you see here, this x defines the point, the n defines the cutting plane. Okay, so the definition of traction vector is a very subtle concept, and it is the starting point of all our subsequent discussions of stresses. Now we have been discussing all of this in the context of the region 1. So what about the region 2? Well, it is very simple. All that you think about is just like these forces are, you can imagine that, you can understand very well that this distribution of forces that are present on the area A, that is actually exerted or brought about due to the interaction with the region 2. So it is actually the region 2 which is exerting these forces on the region 1 over the area A. So whatever forces that we are seeing here, whatever thing we are writing here, that is actually due to the interaction with the region 2. Now, just like the region 2 is exerting forces on the region 1, by Newton's third law, the region 1 is also exerting the same but oppositely directed kind of forces on the region 2. So if we were to consider the counterpart of point P, which is part of this region 2, because note that this is just like an imaginary cutting plane, there would be an exactly same story that we could follow by considering the region 2. However, there is one subtle difference, and that difference is, if you consider this region 2, what about the unit outward normal? Well, I hope it will be immediately clear to all of you that the unit outward normal considering this thing will be minus n hat. This should be perfectly clear to everyone. So the moment you choose your cutting plane, this is n hat, this is minus n hat. Okay, we are just saying that this is the positive one. This is just by convention. Anyway, so because we have this kind of a thing, so considering the region 2, and I'm just not going to the next page because all the diagrams are here. So considering region 2, what we have for the traction vector is, first of all, we are considering the same point P. This is very important. We are considering the same point P. It is like this P is part of this region 1. That same P is also sitting there. Okay, it is like an imaginary plane. So you see, if you, this picture should be clearer. So this P is very much part of region 1. It is also part of region 2. There should not be any confusion about it. So this is the same, the position vector of the same point P we are considering. However, the unit outward normal is the opposite one of what we had considered here. Okay, now we could go into an in-depth discussion of what I'm going to write next, but what I will just say is that following basically following Newton's third law, what we can write is that this is going to be the negative. It is going to be the negative of the traction vector considering the region 1. So the traction vector considering the same point P but sitting on the region 2 will be the negative of the traction vector considering the same point P but within the region 1. So this concept will be something which will be subsequently be using in order to derive some very important formula. Alright, so with this we end the introductory mathematical discussion of stress. Time and again we'll be dealing with this concept of traction. In fact, everything will be built on this, and we'll continue with our discussions in the next part of the lecture. Thank you very much.